Okay, friends, welcome back. This is Wednesday night, Spring Break 2, March the 25th. I wanted to get this video out to you because I know a couple of people have been asking some questions about the upcoming homework due this Sunday because we haven't been together for quite some time. And so I wanted to address all those concerns in this video and also just get us back into the swing of things slowly as to what we're going to expect for next week. And so, yeah, some people brought up a really, really good point that one of the things that I didn't realize, mostly probably because the way that we ended our time together, was that something was missing in order for us to actually be able to do the homework this time round. And that was the concept of electric fields. Right? We talked at length about electric forces, but we didn't really spend a lot of time talking about electric fields. If you remember, we talked about electric field lines, but we didn't talk a lot about electric fields themselves. So I want to knock that out for you right now, get that on the record, and then make sure that we're all on the same page. So let's jump straight to it. Okay, so when we talked about electric force, right, let's remind ourselves what the formula for this guy, right, was. The electric force, we said by definition, is K, Q1, Q2 over the distance between those objects squared, right? And we had a better way of writing this, right? We really said the force that one puts out on two, right, looks something like this. And what do we say again if Q1 is here and Q2 is here? I remind you that R, as always, represents the distance from center to center. Notice that these here are both magnitudes of the forces, right? We are never plugging in values for those like the -10 or -5. We're just plugging in 5 or 10, whatever the case may be. We're always plugging in magnitudes there. That's because, remember, we're going to use those rules that we talked about in order to establish the sign. What are those rules? Well, those rules, what we draw the electric field lines, right? So we said if a charge is positive, right, then we draw its electric field lines emanating outward, and it's in all directions, but typically speaking, the only direction that we ever have to draw is the one that's directed towards where we're actually looking to observe the effect. And we do the opposite if it's negative. So if the charge is positive, the field lines emanate like that. And if the charge is negative, we draw the field lines again from all directions coming in to the particle. And again, what was the motivation for drawing these electric field lines in this way? The motivation is because that assures us that we will always obey the idea that like charges repel and opposites attract, okay? If you do that by simply by plugging in the values into this formula up here, you'll get lost really fast, and you won't necessarily guarantee that the force is doing the direction that it actually tells you to do. This really is the only way to assure that that effect is preserved. Okay, so now that we got that out of the way, why did we call them electric field lines, and how does it relate to this other concept of electric fields? Well, take a look at the formula for force, right? If I'm going to talk about the electric force between two objects, I need two objects, right? One hand, two hand. Then I can talk about what the electric force from the right hand goes on the left hand, okay? But it's a perfectly reasonable question, and sometimes even maybe even more intuitive to say that, well, if hand left was just sitting out in space and it was charged, well, what pattern does it put out? What field does it put out such that if you were then to take another charge and place it next to it, then that would be the resulting force. Why is that a valuable concept for us to have? Is because a lot of times that's what you do in real world situations, right? You have one object sitting out there, maybe it's charged. You say, gee, I wonder what will happen if I place another charge next to it. But before you do that, you typically want to know the prediction beforehand, right? So that's where the difference between electric field versus electric force comes in, right? Namely, when there's just one charge sitting out there, we can talk about the electric field that it puts out, it emanates with these field lines, versus there having to be the presence of a second charge and then talking about the interaction force between the two of them. So let's just get that, a simple definition for that, right? The idea or the concept of an electric field is how the field lines emanate to or from a single body of charge. And obviously that can be a single charge as well, right? Namely, it's the field around the particle such that if we placed a second charge within some distance, again, r center to center, it would then feel the electric force. That means we already then know the equation for this, right? If it's really just the single field or the single thing that one charge puts out without the presence of another charge, right? Let's say we have two particles, 1 and 2, that we were talking about their force between them, right? A way of saying the electric field that's put out by 1 is just F12 divided by charge 2, right? And now that doesn't sound very enlightening, right? Because you're like, well, I thought you said, James, the whole point of having the concept of electric fields was that so we didn't have to first calculate a force between two particles. Well, let's just take that one step further, right? We know what the definition of the force between two particles would be. It would be K, magnitude Q1, magnitude Q2, divided by the distance between R1 and 2 squared, right? And so if we were then dividing by Q2, that would put a Q2 down here. And what do you know? Q2 is going to cancel Q2, leaving us just with K magnitude Q1 over the distance that you would potentially place a particle squared. So if we just remove the subscripts totally, we see that electric field is really an electric force divided by one of the charges, or in general, an electric field is K, the magnitude of its Q, divided by the distance that you would place it squared. Now, a couple things to note. All of our same rules have to apply. Force is a vector, so electric field's got to be a vector, right? Which is where that concept of electric field lines comes from, right? So if I have a charge sitting out in space, Q, and I ask what direction is its electric field, well, it's dictated by the sign of the charge, right? Same rules. You draw its field lines emanating out from the body when it's positive. You draw the field lines emanating into the body when it's negative. So if you understand the concept of electric force, there really is not much of a difference between it and electric field. It's just the field references one charge, what the field would be if you just had this thing here. But in order for you to have a force between two charges, you need two charges, right? This one's effect on this one, or another way of thinking about that is this one's effect on that one, right? Because we know Newton's third law will take care of the way of which force we calculate there. So it really boils down to how you want to represent it, right? What is more convenient at the time, or of course, what is the problem just asking, right? So when I always think about things, my brain always says, well, what is the field something puts out, right? If this thing was sitting out in space and I put something some distance r to it, what would be the force, what would be the field that it puts out? We draw our electric field lines. Then what do you know? If I bring another particle in with some charge and I place it at that distance, then I can talk about the force. It's going to be important for us in another week or so to be able to go back and forth between the two, between field and force. And we're going to see why, because we know where this game goes, right? We have to work with vectors for a while, but then at some point we jump away from vectors and work in just scalars, namely energy. And so obviously if there's some electric force between two things, then we can think of that as an electric bond. There's chemistry, right? Thank you. So there's going to be some sort of potential energy bond between two things. So again, we'll be able to describe the potential, right, of just a single thing, right? 2 versus 1 is going to be a recurring theme when we talk about this stuff. Okay, so that's the background of what I wanted to make sure that we all understood for this piece that I left out from class. Again, it's really not that bad, but I want to make sure that we're all on the same page. Next video that's going to be coming is going to be new content, okay, like real new content. So let's make sure that we're getting ready for that. That'll come out probably sometime end of this week, beginning of next week, or I'm sorry, beginning of the weekend. That way you have plenty of time. So what am I going to do? You stayed this long all the way to the end of the video. What am I going to do about this homework? Yeah, I messed up because there was like 2 problems that had this concept of electric field here. So I'm just going to extend it till next week. It doesn't matter at this point because we're going to get it done regardless, okay? But that means next week you're going to have the homework that was supposed to be due during spring break, and you're going to have another homework on top of it for the new content. Hope that sounds good, ladies and gentlemen. Look forward to seeing you soon. Have a great night.